So hello everyone, welcome back to the Advanced Algorithm playlist. I am Sahil Sawant, currently pursuing M.Tech in Computer Engineering at VJTI, and today I am going to dive into something that pops up everywhere in algorithm, that is the recurrence relations. If you want to master divide and conquer algorithms, the dynamic programming, and understand the complexity of algorithms like merge sort, binary search, quick sort, recurrence are your best friend. So in this video, we will explore what is recurrence relation, why do we need to use them in analysis of algorithms, common forms of recurrence that are used in design and analysis, how to solve them using substitution methods, recursion tree and master theorem. And we are also going to dive into intuitive examples so that we understand as to why they are not just the formulas. तो चलिए शुरू करते हैं. A recurrence relation is way of expressing the running time of an algorithm in terms of its smaller inputs. So in simpler words, मुझे tn का तो नहीं पता, but मुझे t of n by 2 का पता है. And this is exactly how the divide and conquer algorithms works. So tn, which is divided into two parts of tn by 2, and tn by 2 is again divided into two parts of tn by 4, and going on and on. मैं एकदम लास्ट वाले का पता कर सकता हूँ, एंड अगर मुझे लास्ट वाले का पता है तो मुझे टी.एन. का भी पता होगा. सो दिस इज हाउ द रिकरेंस रिलेशन वर्क्स. सो फॉर मेनी एग्जांपल्स लाइक बाइनरी सर्च, द रिकरेंस रिलेशन, द टी ऑफ एन इज गिवन एज टी ऑफ एन बाई 2 plus 1. For merge sort, it is given as 2 times of tn by 2 plus 1. So what exactly does the recurrence means? That the current problem is solution of smaller problems plus some other work that is being performed. अगर हम बाइनरी सर्च का ही देखें, so tn equals to tn by 2 plus 1 जो है, so tn by 2 is solution for the smaller problem and 1 is the work done in dividing the problem. So अगर इसे रियल लाइफ एनालॉजी से हम रिप्लेस करें, let's suppose I am supposed to clean my messy room. I will first of all divide it into two parts, left and right. First of all, I will be cleaning the left part, for which it takes a certain amount of time, certain amount of work into time. Then I'll go to the right part, which will also take a certain amount of work into time. Plus, there will be some extra work in putting everything together. So, what is the total work that I have done? Cleaning the left plus cleaning the right plus the arrangement time. Now many algorithms don't have linear or direct formula to compute the time complexity. For example, sorting using merge, finding the closest pair of points, Tower of Hanoi problem, multiplying matrices. So to solve this problem, we have to break this down into smaller chunks. So recurrence functions can help us mathematically define the algorithm, find the exact complexity and compare performance between these algorithms. It's like having a roadmap of time for every recursive call. Whenever you see a recurrence in your algorithm, do this checklist. Step 1, count how many subproblems the main problem is divided into. Like binary search is divided into one subproblem, merge sort is divided into two subproblems. The second step is to compute the size of each subproblem. So for binary search, the size of each subproblem is n by 2. For merge sort, it is also n by 2. The third step is to calculate the extra work per level. So in binary search, the extra work is going to be constant, while for merge sort, it is going to be n. And the step 4 is going to be combining all these sub-problems to get the bigger picture. So Tn equals to a times of t times n by b, t of n by b plus the extra work that was performed, that is f of n. This is the general structure for a recursive function, where a is number of sub-problems a main problem is divided into, b is the factor by which the input function reduces, and f of n is the extra work that is performed outside. Now moving on to the main part, how we solve these recursion functions. So to solve these recursive functions, there are mainly three methods. The first one is the substitution method, the second is the recursion tree method, and the third one is master theorem, which is the most powerful method in solving the recursive relations. So talking about the first one, that is the substitution method. Here we guess the answer and then try to prove it. For example, if I take a relation T of n equals T of n by 2 plus 1, which is an equation for binary tree, guess is that T of n is going to be log of n. Now moving on to the next part, that is the recursion tree method. So recursion tree method is visual technique that helps us understand how the work is distributed across recursive levels. So let's take the most famous recurrence relation for merge sort, that is T of n equals 2 times of T of n by 2 plus n, which means we split the problem into two smaller problems, that is 2 times of T n by 2, and then we add n amount of extra work that is going to be outside the relation. Now let's expand this relation like a tree. So for level 0, that is the root level, which is also known as the starting level, the total amount of work done is n. Now at level 1, we have two subproblems, each of size n by 2. Work done for each subproblem is n by 2 and total number of subproblems are 2. So total work done at this level is going to be 2 times of n by 2, which is n as well. For the next sub-level, each of these two subproblems are going to split in two halves as well, which are going to be total of 4 subproblems. Now the work per subproblem is n by 4 and number of subproblems are 4. So total work done for each subproblem is also going to be n. So as we look at the general pattern, every level is doing n amount of work. At level 0, it was n level of work. At level 1, it was also n level of work, that is 2 times of n by 2. At level 2, it was also n level of work, which was 4 times of n by 4, which continues until the subproblem is reduced to size of n equals to 1. So how many levels are here that we have divided into? We have divided n. So how many levels have we divided the subproblem into? So first of all, there were n parts, which we divided into n by 2 subproblems, which were later on divided into n by 4, and this continues until we get the last unit as 1. So number of divisions is log of n to the base 2. So the total levels that we get are log of n. Now total work done in the overall process is going to be work done per level multiplied by number of levels, which is n into log of n, which gives us the complexity of theta of n log n. That's why we say the complexity of merge sort is theta of n log n. Moving on to the next concept, that is the master's theorem. The master's theorem helps us understand and solve the recursive relations in the form of T of n equals a times of T of n by b plus f of n, where a was the number of subproblems, b was size reduction factor, and f of n was extra work done outside the recursion. When we compare f of n with n to the power log a to the base b, this quantity tells us how much work recursion relation contributes. So there is this direct comparison. If work is smaller, recursion dominates. If the work done is equal, both contribute equally, and if the outside work is larger, the outer one dominates. Let's break down each case clearly. So the first case is going to be f of n is smaller than log to the power a to the base b. Now in this case, outside work is going to be less, which means the recursion is going to dominate. So think of it like small helper workload versus huge recursive workload. So example of this can be understood as T of n equals 2 times of T of n by 2 plus 1. Here a is going to be 2, b is 2, n to the power log 2 to the base 2, that is n to the power 1, which is going to be n. So f of n equals 1. The result is going to be T of n equals big O or theta of n. In second case, if we consider f of n is equal to n to the power log a to the base b, that is outside work is almost equal to the recursive work. Now both of them contribute equally, so we add log n factor. For example, if t of n equals 2 times of t of n by 2 plus n, here n to the power log 2 to the base 2 is going to be n itself, and f of n here is n, that is same. The result is going to be t of n is theta of n log n. That is why merge sort is having time complexity of n log n. In the third case, f of n is larger than n to the power log a to the base b. That means the outside work dominates the recursion. So in this example, if t of n equals t of n by 2 plus n square, here n to the power log of 1 to the base 2 is going to give us n to the power 0, that is 1. Now f of n equals n square, which is much larger than 1. So the result is going to be t of n equals theta of n square. Understanding it with real life analogy, think of a company structure where CEO is assigning the works. This is your main problem, that is of size n. The manager gives us the sub problems. If CEO gives work to a manager, each handling 1 upon b amount of region, where a is the number of sub problems and b is the division factor. Now office work, that is f of n, this is the extra paperwork the CEO does outside the delegation. Now think of it like in case 1, recursion wins, where managers are doing a lot of work and CEO's extra paperwork, that is f of n, is very small. Now think of this case 1 where recursion wins. Managers are doing a lot of work and CEO's extra paperwork, that is f of n, is very small. That means the managers are carry forwarders of the company. In case 2, let us say there is a tie. Managers and CEOs have equal contributions. That means both are equally busy. And in case 3, where f of n wins, CEO is having huge paperwork and managers are doing much less. That means the outside work of paperwork, f of n, dominates more than the managers. That is exactly how master theorems picks between recursion work, outside work, or both doing equally. This is the simple company analogy that makes the theorem more intuitive. So in today's topic, we have covered what recursion relations are, why they matter, how to form them, methods to solve them, master theorem, and real life analogies. In the next lecture, we will solve multiple recursion problems exactly like how they appear in exams or interviews. If you enjoyed this video, hit that like button, subscribe to the channel and share it with your batchmates and juniors in CS, IT or AI fields.